welcome to the deep dive. Today, we're looking at something truly surprising in the world of advanced AI. It's about those impressive thinking steps we see from large language models. The intermediate bits they generate before the final answer.
Right, the reasoning traces.
Exactly. And it turns out they might not be thinking in the way we instinctively imagine at all. We've got some fascinating research here that's really flipping assumptions.
It really is. There's been so much excitement around these intermediate steps. The idea, is that when models like, say, DeepSeek's R1 show their work, it feels like they're genuinely understanding the problem.
Like how humans show their math steps.
Precisely. And some models even output things like, aha, remember that with R1. It felt like a real moment of insight. These steps are just sequences of text the model spits out before the final answer, maybe breaking down the problem or listing options.
It really does feel like you're getting a peek inside the AI's head, doesn't it? But the big question we're diving into for you today is, are these steps actually the key? Are they truly necessary for the model to get the right answer?
Or is something else entirely going on?
Right.
And it's a genuinely tough puzzle, especially with these massive models, billions of parameters trained on just unimaginable amounts of data.
Yeah, understanding the internals is complex.
Hugely complex. Like trying to map a city by looking at every single brick. It's just not practical for these big systems.
Which is why this research we're looking at took such a clever approach. Instead of wrestling with the giant LLMs, they scaled it down. They used smaller, fully controlled models and give them a very specific, well-defined problem.
Which was?
Finding the shortest path in a maze using the A-search algorithm.
Ah, okay. A classic computer science problem.
Exactly. And what's so smart about this is that it lets you analyze everything rigorously. Both the final answer, did it find the shortest path, and those intermediate steps.
Because in this case, the reasoning is supposed to be the steps of the A algorithm itself.
Yes, and A follows very specific rules. So the researchers could actually build a formal way, like a checker, to see if the model was following those A rules correctly in its intermediate steps.
That's the key difference. You can validate it properly, unlike vague natural language reasoning.
Okay, so before we hit the really surprising results, let's just quickly touch on why people thought these reasoning traces were so important in the first place.
Well, the common sense idea, the intuition, is that if you train a model on examples of correct reasoning, you show it the step-by-step process. Like for A, you're actually teaching it how to solve the problem.
Not just memorizing answers.
Exactly. You're teaching the process. There was earlier work, things like SearchFormer and Stream of Search, that did exactly this. They trained models on these algorithmic execution traces.
Trying to get the model to internalize the problem-solving method itself.
Right, like teaching math methods, not just answers.
Okay, so this new research builds on that, but adds this formal validator for the A traces. Let's unpack that a bit. How does this validator actually work? How can it check the AI's reasoning?
It's quite clever. They essentially built a system that simulates the core components of the A algorithm, the open list, the closed list, based only on the trace the model generates.
Okay.
And it goes through step by step, checking for all sorts of errors, like basic parsing issues. Does the output even look like an A command? Or invalid moves, like trying to path through a wall in the maze.
So it's like a really strict rule checker for the A language.
You got it. And it catches more subtle things, too, like did the model try to close a node it already closed? Did it try to close something that wasn't even on its to-do list, the open list?
Well,
Or even, did it choose to close a node when there was actually a better, more promising node still waiting on the open list according to the A rules? And, crucially, does it eventually find and correctly identify the goal?
wow, that's thorough.
It really is, and it highlights why this is so hard with natural language reasoning. It's just too fuzzy. You can state a valid reasoning step in so many ways.
Right, ambiguity. But here, with A, it's precise. Okay, so they have this validator. What happens when they compare the trace validity, how correct the reasoning looks, with the final outcome, whether the model actually found the shortest path?
And here's where things start to get really interesting. This is the first big surprise. They found the link between trace validity and solution accuracy was, well, pretty loose.
Loose? How so?
Basically, models could produce perfectly valid A traces, according to the validator, ticking all the boxes, but still end up recommending the wrong path. And conversely, sometimes models would generate traces with clear errors in the A logic, yet they somehow still managed to find the correct shortest path in the end.
So the correct thinking didn't guarantee the right answer, and wrong thinking could still lead there.
Exactly. They point to figure 3 in the paper, and it shows this disconnect visually. Lots of cases where valid traces lead to wrong answers, and invalid traces lead to right ones. It already starts to chip away at the idea that the trace is the reasoning process leading to the answer.
That's definitely counterintuitive. But then they push it even further, right? With this experiment they called the swap data set. Tell us about that.
Right, this is where they really went for it, directly testing if the meaning or semantic content of the trace matters at all.
Okay.
They took their mazes and the correct shortest paths, but then they paired each correct solution with a completely unrelated A trace.
Unrelated how?
They took a valid A trace from a different maze entirely and randomly shuffled its steps. Then they paired that jumbled, irrelevant trace with the correct solution for the original maze.
Whoa, wait. So the trace looks structurally like A steps, create, close, nodes, etc., but it have absolutely nothing to do with the maze the model is actually trying to solve. It's just noise.
Complete noise in terms of relevance to the current problem. It's semantically meaningless for that specific maze. Pure gibberish in context.
Okay, that sounds crazy. What on earth happened when they trained models on that? Correct answers paired with totally irrelevant, nonsensical reasoning.
This is the kicker. The results were, well, astonishing. These models trained on nonsense traces didn't just do okay. They performed just as well as the models trained on the correct A traces on the mazes they'd seen before, and sometimes even better than the baseline model trained only on solutions.
As well, with random gibberish traces.
Yes. And crucially, they often generalize better to new, unseen mazes, especially mazes created using different algorithms, presenting different kinds of challenges.
Better generalization from incorrect traces?
Significantly better in some cases. For example, on mazes from a drunkard's walk generator, the model trained on the swapped, totally wrong traces got 26% accuracy. The model trained on the correct traces, only 2.5%.
26 versus 2.5. That's staggering.
It is. And of course, the trace validity score for that swapped model was 0. Utterly 0. Table 1 in the paper lays it all out. It's a dramatic difference. Training with the wrong reasoning sometimes led to better out-of-distribution performance.
Okay, my brain hurts a little.
Yeah.
That completely shreds the simple idea that the intermediate steps are useful because they represent meaningful reasoning, doesn't it?
It really, really does. It makes it very hard to argue that the model is succeeding because it's thinking through the problem using those steps, if steps that are total nonsense work just as well, or even better.
So we really need to be careful about anthropomorphizing these outputs as thoughts.
Extremely careful. If irrelevant content works, the meaning we perceive might not be the functional reason for their effectiveness at all.
Okay, so if it's not about following the algorithm or meaningful steps, what is going on? What's the alternative explanation? The researchers talked about prompt augmentation.
Yes, that's their hypothesis, and it's a really interesting one. They suggest that the act of generating these intermediate tokens, regardless of their content, apparently functions as a kind of learned technique to augment the input, like a sophisticated, internally generated prompt.
Huh. So the model isn't necessarily reasoning with the trace, but generating the trace changes something about how it processes the original problem.
Exactly. Think of it this way. Maybe for any given task, there's an optimal way to phrase or add to the initial prompt to help the model perform better. It might not be intuitive to us.
Like finding the magic words.
Kind of. And the idea here is that training the model to produce these traces, even nonsensical ones, teaches it to automatically perform some kind of beneficial internal transformation or augmentation on the input before it gives the final answer.
So it learns to rewrite the problem for itself, in a way, even if the rewrite looks like junk to us.
That's the gist. It's an internal adjustment that helps guide it to the solution, even if we can't easily interpret that adjustment as meaningful reasoning.
It does make me think of those adversarial prompt examples, where adding weird characters or nonsense phrases can suddenly make a model answer a question it previously couldn't, or vice versa.
Absolutely. There's a strong parallel. We know from adversarial prompting that seemingly meaningless additions can drastically change model behavior. This research suggests that maybe these reasoning traces are a more structured, learned version of that phenomenon, an internal prompt manipulation.
Fascinating. So stepping back, thinking about the big picture, those huge cutting-edge LLMs everyone's talking about, what are the major implications here?
Well, the big takeaway, I think, is that the amazing performance we see from models generating these long chains of thought might not be because they're genuinely reasoning in a way we understand or even faithfully following some internal algorithm.
The effectiveness might come from somewhere else.
Exactly. This study strongly suggests the act of generating tokens, the process itself, might be more about the model finding a useful way to structure its computation or augment its input rather than the semantic content of those tokens being the key.
And focusing purely on whether the trace looks logical to us could be misleading if we're trying to understand how they actually work.
Very potentially misleading, yes.
Okay, so for you, the listener, wrapping your head around this,
Hmm.
the key insight is that the impressive power of these reasoning models might not be because they think like us step by step.
Hmm.
Those intermediate traces could be acting more like an internal tune-up, a way to enhance the prompt and their literal meaning. Maybe not as crucial as we thought.
Which leaves us with a really provocative question to chew on, doesn't it? If the content of the reasoning steps doesn't always matter for success, what does that truly tell us about how these complex systems learn and solve problems?
Yeah.
Are we maybe, by focusing so much on making AI reasoning look human and interpretable, actually holding back the development of even more capable, maybe completely alien forms of AI intelligence?
That's definitely something to mull over. Could interpretability be a cage we're building?
It's a possibility worth considering.
Absolutely. Well, if you want to dive even deeper into the nuts and bolts of this, we strongly recommend checking out the original research paper. It's packed with details that really make you question assumptions.
Definitely worth a read.
Thanks for joining us on this deep dive.